Now that you have had a chance to think about how to generalize the peak counting algorithm, let us take a look at the algorithm that I came up with and turn it into Python code. What you see here is my algorithm, but I want to note that you can come up with a variety of different algorithms that are still correct. So you may have come up with an algorithm that looks very different that could still be perfectly fine. In my algorithm, I start with a peak count of 0. Then I count from 0 to the length of the data. I call each number I. If the ith element of my data is a peak, I'm going to increment my peak count. As a quick reminder, remember that increment means make it one more, so peak count equals peak count plus 1. After I finish counting, my answer at the end is going to be the peak count. Now, we said we need to figure out if the ith element is a peak. If we wanted to test this by hand, we might have a little more complicated example than we had before where our peaks were pretty clear. Is this a peak right here at 163? It's higher than the points around it, but it's also not really that high compared to this other peak. So maybe this is a little bit of measurement error rather than a true peak. Eventually, we are going to have to precisely state what we mean by a peak to have working code. But for the moment, we want to know if this algorithm is right, assuming that we can correctly determine where there's a peak. If you try it out on a few cases, you will find that it works well. So now we want to turn this algorithm into code. We start by declaring our function, which takes one parameter, the data to analyze. Our algorithm starts with a peak count being 0, so that will translate in assigning 0 to peak count. That part should already be fairly familiar. Next, we want to count, so we want a for loop. You have seen range-based for loops before, though you may not have used them as much. Here, we want to use len of data to find out how many elements are in data. Then we use range of len of data to get the sequence of numbers from 0 to that length. Next, our algorithm asks us to make a decision. Is there a peak at this index? As we want to make a decision, we need an if statement. We also know that figuring out whether or not there is a peak at this particular place is a bit of a complex step. Accordingly, we are going to just write a function call and solve that problem later. We will assume that isPeakAt works correctly and proceed. Then, once we finish this translation to code, we will go back and do the 7 steps for the isPeakAt problem. You may wonder why I decided to pass data and I to isPeakAt rather than just data at I. We will talk about that in a moment. The next step in our algorithm is to increment peak count. We can translate this step to peak count equals peak count plus 1. After our loop, we need to return our answer. Now we are done translating this algorithm to Python, but let us take a moment to talk about why I used a loop over the indices rather than just iterating over each element of the data, and why I passed the data and index to isPeakAt. Or, put a different way, why did we not just do this? I'm thinking ahead a little bit to what I will want to do for isPeakAt. Even though I have not thought through the entire problem, it seems like isPeakAt will need more than just a single value from the data. For example, if we just passed it one value, like 162, we can't really answer the question. On the left, we have a value of 162 where the answer is yes, but we also have other places where the heart rate of 162 was not a peak. However, if we look at this and think about the question, is there a peak at 2 seconds or is there a peak at 6 seconds, we see that this is a question we can answer. This observation tells me that we will want to pass the data and index to isPeakAt. With this algorithm translated to Python, all that is left to do to solve this problem is to write the isPeakAt function. We will want to go through the 7 steps to come up with an algorithm, translate it to code, test it, and debug it.